Welcome back to the Week 5 lecture. This week we will be covering Chapter 17 on change of phase. During this week we'll be covering Chapter 17 through this lecture. You'll be reading Chapter 17, completing the Chapter 16 and 17 homework through Mastering Physics, complete your Week 5 discussion, your Week 5 lab, and you'll be doing a lab report on this lab, which is due next week. As a bonus for Week 5, I'm going to let you skip one lab assignment during Weeks 5 through 10, so you can choose the Week 5, 6, 7, 8, or 9 or 10 lab. If you choose to skip this week's lab, then next week your lab report will be done on the crushing cans lab, since you didn't do this lab. So you do need to still do a lab report next week if you choose to skip this lab. On the other hand, you could choose to do the lab this week, skip the lab report, any of those that you want to skip. And in the week that you decide to skip the assignment, you'll just go to the assignment link, and instead of submitting an assignment, you'll just enter in the text, I am choosing to skip this assignment, to let me know that you are skipping the assignment and to not deduct those points against you. In this lecture, we're going to be covering phases of matter, evaporation, condensation, boiling, melting and freezing, and energy and changes of phase. So matter exists in 4 common phases that involve transfer of internal energy. So the amount of energy that's in a substance determines what phase it is, whether it's a solid, a liquid, a gas, or a plasma. And a solid phase, if we look at water, water is a solid, is what we call ice. Water is a liquid, is just liquid water. Water is a gas, would be vapor, water vapor. And then a plasma is when a vapor disintegrates into ions and electrons. And we'll go into a little bit later on what exactly a plasma is. So matter can be any of these 4 phases, and we'll go over on the upcoming slides what makes matter be one of these phases. When we use the term phase, that means is it in a solid phase, a liquid phase, a gas phase, or a plasma phase. And the phase that something's in depends on the temperature and the pressure. To change from a solid to a liquid, or a liquid to a gas, or a gas to a plasma, means that you have added more energy to the material. So either more energy through a higher temperature or a higher pressure. So a solid has the least amount of energy. To go to a liquid, that means we've added either temperature and or pressure. A gas means we've added more temperature or pressure. So if you think of a solid like ice, it's cold. A liquid is not going to be quite as cold as ice. You've added some temperature, and there is also less pressure. And then to go to a gas, there's even less pressure and even a higher temperature. And then to get to a plasma, even a higher temperature would be required to take you to a plasma. So energy causes the molecules to move more rapidly. Now, when something evaporates, it's going from a liquid into a gas, and what happens is as you add more temperature, those molecules start moving faster and faster and bouncing off each other more rapidly and spreading apart. And as the molecules spread apart, they go from being a liquid, where you have a lot of water molecules close together, to a vapor, where the molecules are dispersed in the air. Now, opposite from that, if you were to take your water vapor and let it cool down, the molecules would start moving more slowly. They would not bounce off of each other as hard. They would be able to move a little closer together, and they would condensate back into liquid. So if we move from a liquid to a gas, that's evaporation, and a gas to a liquid is called condensation. Molecules in a liquid move randomly at various speeds, continually colliding with one another. Some molecules can gain kinetic energy, while others will lose kinetic energy during their collision. So the molecules in a liquid are constantly moving around and hitting each other. Some energetic molecules escape from the liquid and become gas if they get enough energy. And that's again because they're able to bounce far enough away and separate themselves from the other water molecules. The average kinetic energy of the remaining molecules in the liquid decreases, resulting in cooler water. So if one water molecule with a lot of energy evaporates and moves away, it takes some of that energy in the form of heat away from the liquid, and the liquid becomes a little bit cooler. This is why a lot of animals will use something such as sweating or rolling in the mud and letting water evaporate off them to cool themselves. Because when water evaporates from us and takes some of that heat with us, our bodies cool down. And that's why when you sweat and the sweat evaporates, you cool down. Pigs that can't sweat will roll in the mud, and that water will evaporate off of them and let them cool down. Sublimation is when you change directly from a solid to a gas. So normally you would go solid, liquid, gas, but when you go from a solid directly to a gas, like dry ice, they call this sublimation. As we talked about a couple slides ago, condensation is when you go, it's the opposite of evaporation, when you go from a gas to a liquid, and gas molecules near the surface are attracted to the liquid, and when the gas molecules bounce around, the ones that hit this liquid can become attached or bond to these water molecules in the liquid and go back into the liquid. Kinetic energy is then absorbed by the liquid, so those water molecules that were in the air and move into the liquid, that kinetic energy is absorbed by the liquid, and the temperature will go up. So an example is steam releases much energy when it condenses to a liquid and moistens the skin. Hence, it produces a more damaging burn than that from the same temperature boiling water. So if you ever put your hand over steam, it can feel very, very hot, more hot than if you were that same temperature if you were to just stick your hand in that same temperature water. And that's why steam can easily burn you. And you'll feel warmer in a moist shower stall because of the rate of condensation exceeds the rate of evaporation. So just standing in that warm, moist air, that's why it feels more, you feel hotter when it's a more humid day than when it's a drier day. Some more examples of condensation. In dry cities, the rate of evaporation from your skin is greater than the rate of condensation, so you feel colder. And if you live around Klamath Falls, this would definitely apply to you in that area. In humid cities, the rate of evaporation from your skin is less than the rate of condensation, so you feel warmer. And a cold soda pop can is wet in warm air because slow-moving molecules make contact with the cold surface and condense. So that's why if you have a cold soda pop can on a hot summer day, it will make condensation on the soda can. Condensation also occurs in the atmosphere. When the temperature of the atmosphere is low, the water molecules in the air move slowly, and slow-moving water molecules will stick together and cause condensation. An example is fog and clouds being created when air rises and the water molecules stick together. Let's do a review question here. If bits of coal do not stick to your feet when fire walking, it's best if your feet are, do you want them to be wet, dry, sort of wet and sort of dry, or none of these? You want your feet to be wet. So the energy that vaporizes water is energy that doesn't burn your feet. The review question, when you step out after a hot shower, you feel cold, but you can feel warm again if you step back in the shower area. Which process is responsible for this? Evaporation, condensation, both of these, or none of these? And the answer is condensation. When you step back into the shower area, the steam that is present condenses on your body, causing it to warm up. Next, let's look at boiling. So boiling is a rapid evaporation from beneath the surface of a liquid. Forces due to combined pressure of the atmosphere and water will result in the water boiling. So rapid form of evaporation beneath the surface forms vapor bubbles. And vapor bubbles will rise to the surface. If the vapor pressure of the bubbles is less than the surrounding pressure, the bubbles collapse. Hence, the bubbles don't form at temperatures below the boiling point, and vapor pressure is where vapor pressure is insufficient. Boiling water at 100 degrees Celsius is in thermal boiling water at 100 degrees Celsius is in thermal equilibrium. Boiling water is being cooled as fast as it is being warmed. In this sense, boiling is a cooling process. So even though boiling occurs at a high temperature, the boiling will actually give off heat and cool the water if you didn't continue to heat up the water. Example, buildup of vapor pressure inside a pressure cooker prevents boiling, thus resulting in a higher temperature that cooks the food. So when you're in a pressure cooker, you are keeping that pressure in the pot. The boiling can't occur to release that heat, and so you get a very high temperature, higher than if you just cooked the food in the same pot over the same temperature burner. The boiling point is lower with lower atmospheric pressure. So water will boil at 95 degrees Celsius in Denver, Colorado, a high altitude, instead of at 100 degrees Celsius at sea level. So the higher you go up in elevation, the lower temperature that you need to boil water, because there is lower pressure, the high atmospheric pressure, the higher up you go. Let's do some more review questions. The process of boiling. A, cools the water being boiled. B, depends on the atmospheric pressure. C, is a change of phase below the water surface, or all of the above. The answer is all of the above. So boiling cools the water. The temperature at which you're going to boil depends on atmospheric pressure, and it is a change of phase that occurs below the water surface. Melting occurs when a substance changes phase from a solid to a liquid. It's the opposite of freezing. And when heat is supplied to a solid, the added vibration, so heat causes the molecules to vibrate and move, this added vibration breaks the molecules loose from their solid structure, and you get melting. Freezing occurs when a liquid changes to a solid. It's the opposite of melting. And when energy is continually removed from a liquid, so when heat's removed, the molecules slow down until the forces of attraction bind them together and they form a solid. Moving from a solid to a liquid to a gas requires added energy. So you have to add energy to move from a solid to a liquid to a gas. To move the other direction from a gas to a liquid to a solid requires that you remove energy. So energy is absorbed when the change of phase is in this direction. So you're absorbing energy, getting warmer and warmer and warmer when you go this way. When you go to the left from a gas to a liquid to a solid, then energy is released and it gets cooler. Some different ways that we can measure energy are the calorie and the joule. And a calorie is the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. And a calorie is equal to 4.2 joules. So it takes about 4.2 joules of energy to raise 1 gram of water by 1 degree Celsius. Food calories, if you're thinking you've heard the term calorie, it's most likely where you've heard it from. And a food calorie is actually a kilocalorie. So for example, 1 food calorie is equal to 1,000 energy or heat calories. Calories in food are measured by burning up the food and then measuring the change in heat and temperature to determine the number of calories or energy given off by that food. Let's look at a couple examples of vaporation and condensation. So in your refrigerator, the cooling cycle of the refrigerator pumps a special fluid that vaporizes and draws heat from the stored food. And the gas that forms along with the energy that it absorbs is directed to the condensation coils outside the fridge. And this heat that it absorbed from the food is released, and the fluid then condenses back to a liquid. And so you keep repeating that cycle and you keep removing heat from your food, making it colder and colder. An air conditioner pump pumps heat energy from one part of the unit to another. So a similar process to remove heat to make it cooler and then pump the cool air throughout your house. Heat of fusion is the amount of energy that you need to change a substance from a solid to a liquid. So the heat of fusion for water is 334 joules per gram, which means it takes 334 joules of energy for every gram of water to change it from a solid to a liquid. So you have to put that much energy in for every gram of water that you have to get from a solid to a liquid. A tip using this idea is that in cold climates you can replace frozen tubs of water with unfrozen ones in your cellar to prevent jars of food from freezing. So if you keep taking the frozen tub that's is very cold and you keep replacing it with an unfrozen tub, then the process of the tub freezing will release heat to the rest of the room and will leave the room warmer while the cold is in that tub of ice. And if you keep taking out that cold tub of ice, you can keep your cellar from freezing. Heat of vaporization is the amount of energy needed to change any substance from a liquid to a gas, or vice versa. Heat of vaporization for water to get from a liquid to a gas is 2,256 joules per gram. So for every gram of water, you have to add 2,256 joules to each gram to change from a liquid to a gas. So a lot more energy required to go from a liquid to a gas than was required to go from a solid to a liquid. If you briefly touch a hot skillet, energy that would normally flow into your finger is vaporized into water, and hence you're not burned. So that's why you can touch something very quickly and not get burned. And whereas if you touched it for a long time, you would get burned. Another review question: when snow forms in clouds, the surrounding air is cooled, warmed, insulated, or thermally conducting? And the answer is warmed. The change of phase from a gas to a solid releases energy, so the surrounding air gets warmed. Next we have which involves the greatest number of calories, and a calorie is just a measure of energy. So which requires the greatest amount of energy: condensing 1 gram of 100-degree steam to 100-degree water, cooling 1 gram of 100-degree water to 1 gram of 0-degree ice, cooling 1 gram of 0-degree ice to near absolute zero, or all about the same. The answer is condensing 1 gram of 100-degree steam to 100-degree water. So 540 calories is more than the 100 calories for B, and half of the 273 calories to cool ice. The specific heat for ice is about half of that for liquid water. If ice is put in a picnic cooler to speed up the cooling cans of the beverage, it's important that the ice melts, is prevented from melting, be in large chunks, or none of the above. The answer is melts. For each gram of ice that melts, 540 calories is taken from the beverage. And that is the end of our week 5 lecture. I'll be in touch with you again in week 6.